work is a clean view. And moreover, got even worse when we are plotting the complete Fourier. So something is different aids and so on, not typically doing. That becomes obvious that there's a learning experience and information. Sorry. And we get those coverage and regularizations. I mean, non-trivial type operations can introduce regularizations, but well, RML on the other way, there is also give us a way out. Typically, these excellent super resolving images with a forward approach, and of course, the forward approach comes with a lot of advantages that we can use more advanced and more sophisticated data terms. And we are not relying on the gridding anymore. And so and it's also very flexible, but what we typically see that there are many hyperparameters which then end up with parameter spaces. So if possible, then it would be very desired that we would have a blind and automatic data visibility pipeline with much fewer parameters and the same quality of the image. And this is where our new idea of a multiscale dictionary comes in. So what will we want to achieve in our final image? So we want to introduce some regularization, which is quite easy in the areas where we have a lot of data points. Well, there's, let's say, we want to go to a chi-square of equal to 1, already a good criterion. But there are also big gaps. And these are coming from uncovered scales, so we need some control over them. This is what regularization translated in the Fourier domain really means. And so we designed a new version of wavelets, which are these famous Mexican wavelets, can be approximated at different absorption functions. And if you, well, this is a 1D representation, I think you can all imagine how this looks in 2 dimensions, just rotating it around. And if you take the Fourier transform of them, they give you Gaussian filters in the Fourier domain. And you can, well, just fit the widths of these Gaussian filters so that they are fit into the UV coverage. So you have different scales that are most sensitive to different parts of your UV coverage. And you even have scales that are most sensitive to gaps in your UV coverage. And what we also see, what is pretty clear when we look for the 27% these different scales typically compress different parts of the information of the complete image. So the biggest scales compress information of well, Gaussian block with the correct size of, let's say, 50 microarcsecond. Then we have some intermediate scales which more or less give us the central depression, and we have the smaller scales where we see the feature of the asymmetry, for example. And this is, of course, not the complete story. When we want to fit our dictionaries of basis functions to the UV coverage, it's not enough to only use radial symmetric methods. We also need to have something which is more more direction dependent, which is quite easy to extrapolate there, as we have already the radial symmetric wave that's already designed by different Gaussian functions. It's very, very native to go to different elliptical functions when we want to have direction dependent. And moreover, when we want to fit our basis functions, our atoms to the UV coverage, what we want to have in the Fourier domain are heavy side mass, so step-like functions, not these Gaussian filters, which also come with a great advantage of these functions are basically orthogonal because they have non-overlapping support in the Fourier domain. And orthogonality is, of course, a big advantage because then you don't have the problem of over-representation of the final image anymore. But I think what we desire from our scales in the image domain is a bit different. So our wavelets in image domain should be smooth, they should have no side clouds, and they should contain, if possible, only positive fluxes. And this is obviously a contradiction. So every wavelet that is orthogonal from each other has to have this very wide cycle. So you can see here the different suppressive functions. And what we can do is we can fit just the central beam, which then insert some technical switch between different dictionaries. So this is part of the second paper that we will go into more details in this. So the final optimization problem then looks like this, where we have the data fidelity terms, which are kind of calibration independent. So it's a closure phase and the closure amplitude. Again, the statement that these are calibration independent is, a bit and what comes in now is gamma or wavelet dictionary. So what we are recovering here is the coefficient array of our terms of our wavelets, and not the final image. What we are penalizing this with a zero term, which is sparsity promoting. I mean, typically you do sparsity promoting with L1, which is of course a convex approximation to a zero. When you really want to have a zero, you could do something like iterative reweighted L1 regularization or something like that. But in practice, we have seen that a zero really gives us the best results here. And so the proximal point operator of a zero functional is in the end just the hard threshold operator, while the proximal point operator of the one functional is the soft threshold parameter. And so it's very, very similar. But what we then recognize is, well, the first three terms are completely invariant against rescaling the flux. Because when you just rescale your complete array with a constant factor, the closure amplitude, the closure phases, and of course the zero term, which is just the number of non-zero coefficients, doesn't change. And so we are also introducing here the total flux constraint to keep the contrast in the images. The problem is that this objective functional is neither convex nor smooth. So it's a bit difficult to find a really converging optimization algorithm here. But what works in our way is the proximal point-based forward-backward splitting, which the technical reason behind this is that the somewhat technical Kodik-Kalinovich property is satisfied with this kind of objective functional. So you can more or less separate this in the smooth and then the convex. Then you can show that in a alternating projection setup, it's still convergent. So in principle, we can run our algorithm from scratch, but the best performance was shown when we have a good initial guess, and we computed this good initial guess just with VHDL without any penalization term. What we have seen then is we also added the last zero to the conf edits, and it was not measured before. What we've seen that for such a synthetic image with photon ring and the shadow, you see a couple of artifacts still in the image when we did VHDL without any penalization, which is quite obvious because there was no regularization introduced. And then we can decompose it into different scales. And from this point to this point, we minimize this objective functional, and we see, okay, these different scales that are like the biggest two that are compressing the information of the shadow, they are running through. Also the smallest scale, which is compressing the information of the ring that we overpose, that's also coming through the algorithm. While all the intermediate scales, where we see a lot of artifacts in the image, they are suppressed by the algorithm. Yes, so coming to my conclusion. So on the left-hand side, you can see a couple of geometric models and a couple of synthetic imaging here. Within the second line, our reconstruction is an RML reconstruction that were done in HDL for reconstruction. And you see that the results are pretty comparable. On the right-hand side, so this is some data set from the ngEHT analysis challenge. So what we are getting in the end is a super resolving super resolving algorithm with some very good representation also of uniform extended division, as we can see in this images. So we are introducing effective regularization, but the main selling point is that we only have one parameter. This was this alpha that was describing how much we threshold every wavelet parameter. So what we are doing here is pretty much data-driven, is blind, and can be seen as a major step in the direction of doing something more automatic imaging. We can probably use this algorithm as a black box to get a good initial guess or a good first starting point for more flexible other imaging algorithms. And in the end, what we also were thinking that this is, of course, giving us some kind of a robust discovery of characteristics or instructional patterns. As we are suppressing information in the gaps and we are highlighting information in the covered regions, this is, of course, something like, well, similar to trying to express in an analytical way what Bayesian methods are doing by sampling. So what we are getting in the end is are really structural patterns that are measured and not just interpolated in the gaps in the municipality. Well, there's a nice byproduct, which is a software with a creative name Mr. B, because talking a lot of beams. And well, among the different imaging algorithms, so I was now talking about the fit. We also have a key variant of it, just to be a bit more kind to the still large clean community. Or there's also a neural network version. We have a new software which is actually it's a package for general complex optimization problems, which by now has attracted interest from many different communities. Attracted commercial interest in medical imaging, for example, is used in material seismology, legal scheduling, biophysics, and so on. So it's really a powerful software that was kind of a byproduct. And what, of course, we have just realized during this meeting here is that we can just use our algorithm as a post-processing tool to separate robust features and interpolated features in already recovered images and movies, just to see are the features that we see in the images and in the recovered movies, are they really there, or have we added them to some very strong bias in the modeling or in the imaging? Yeah, and thank you for your attention, and I'm happy to answer.
Thanks, Hendrik. Are there any questions? We have time for a couple of questions. Kazu.
Yeah, so this is great work, because I'm also interested in a little bit. So I have just a couple of questions. The first one is, so you were actually solving the coefficient, right? The bigger coefficient, rather than the intensity.
Yeah, I mean, the array that we want to recover is the array of wavelet coefficients.
Yeah.
Then we, of course, have to apply our dictionary once more to get.
Yeah, so I think the general approach to solving coefficient often have difficulties to impose like physical constraint and actual image, the image brightness, like no negative constraint I, or some constraint Q and U and V. So how actually do you handle after this? So when you actually start solving coefficient, coefficient doesn't often provide guarantee that the slope sign is, for instance, non-negative. So this is one question, and also second thing is that the wavelet imaging now actually really explored in the last decade. EVIS is actually one of the pioneer. Why actually did you take that as a particular basis? The community actually explored a lot of orthogonal basis and also over complete basis. Is there a reason why actually you picked this particular basis?
Yeah, so okay, to your first question, non-negativity is not implemented in the algorithm by now, but will come in the next months due to an active passive set strategy, where you have the active set of coefficients and the passive set of coefficients pretty similar to how you would implement a semi-smooth IRGNM algorithm. Yeah, it's not so important whether you have a dictionary still in between. And we took these wavelets because they were most easiest for us to fit to the UV coverage. What you typically have are these true wavelets, where this is a wavelet that is kind of the backbone behind the PNG image format, where you have to compress information to get in a compressed smaller size to store them. But the true wavelet has a problem that is upsampling by construction with a factor of 2. So you have only 1 pixel, 2 pixel, next filter size is 4 pixels and 8 pixels and so on. This is of course not flexible enough to fit to the UV coverage. So we just looked at how are these wavelets looking like. And we saw, okay, these are more or less Mexican head wavelets. Well, then we can approximate them by a difference of Gaussian, which is pretty known approximation. And the difference of Gaussian has a nice property that we of course can just scale the Gaussians in the